Hi everyone, I'm McNamara here with the SWOSU Mathematics Department, and I would like to welcome you to the first SWOSU Mathematics Seminar for the fall 2021 semester. This course of talks by faculty is intended to be accessible to undergraduate students and introduce them to some topics that bridge the gap between their undergraduate coursework and mathematics research. In this presentation, I'm going to talk about the mathematics of symmetry. Students who have exposure to the ideas of linear algebra will probably get the most out of this particular session. We do talk about linear transformations, we talk about matrices, so familiarity with those ideas would be helpful. All right, so I wanted to talk about the mathematics of symmetry. So JC will actually be somewhat familiar with this because we talked about symmetry a lot in our summer course.
Oh.
Okay, now Emma, you haven't taken linear yet, no, but you're in modern?
Yeah.
Okay, so, yeah, okay. So the mathematics of symmetry. Come on, buddy, you were working before. Okay, I guess I can just. Okay. So I've got my sections here. So we'll start out with a little introduction. Okay, now it's working. Great. So let's just start out with a question. So what makes a figure symmetric? So I've got figures here, and without me telling you what I mean by most symmetric, which figure is the most symmetric?
Circle. Okay,
so Emma says the circle. Anybody disagree with that?
I do.
You do? What do you think is the most symmetric?
Now I'm like, everybody's looking at me, the square?
Okay, so you think the square is the most symmetric. Any other ideas? Okay, so I mean, I've got my own ranking over here. Least symmetric to most symmetric. So my ranking would have been the trapezoid is the least symmetric, the rectangle and rhombus are tied. That triangle, which was actually an equilateral triangle, was next, followed by the square, the octagon, and then the circle.
Number 5.
We're tied. There is no 5.
5 and 6 is together.
Yeah.
Oh, I didn't even read that.
So if there's a tie for second and third place, then you both get third place. You both lose. So they're tied for 6th place.
So tell me why the circle is.
Okay. I'm glad you asked. What I meant by more symmetric is a figure is more symmetric if there are more transformations that leave the figure unchanged.
Oh.
So the trapezoid that I ranked least symmetric, I guess you could say it has just one. The only thing you can do is you can flip it left to right. You can reflect the figure about this line. And for the purposes of this and what follows, I consider doing nothing a symmetry. And all mathematicians consider doing nothing to be doing something. So I guess we can say there's 2 symmetries. You can flip about that line, or you can leave it completely alone. You can't flip it vertically, because if you flip it vertically, then the long side is up top and the short side is on the bottom. So you can tell there has been a change. Okay, so the equilateral triangle, for example, I would count 6 symmetries. There are 3 rotational symmetries if you count the 360 rotation, which is equivalent to not doing anything. And any of the lines bisecting the angles will give you a line of symmetry. So you can reflect about this vertical line, you can reflect about either of those, and you have a symmetry of the equilateral triangle. So that has 6 symmetries. So that's why I would rank it as more symmetric. All right. So getting back to our ranking here, this is why I rank the circle as most symmetric. The circle would have infinitely many symmetries. These figures have increasingly more symmetries, but none of them would have as much as a circle. So with the equilateral triangle, you have 6 symmetries, 3 rotations, 3 lines of reflection. So your rotations would be 120, 240, and then not doing anything. Okay, but for the circle, if you rotate by any angle, you would get a symmetry. So any angle of rotation would be a symmetry for the circle. And these guys, like the equilateral triangle, would have lines that go through one of the vertices perpendicular to the opposite side. That would be a line of symmetry. The square would be, has the left to right line, the vertical line, and the 2 diagonals would be symmetries. The octagon, I think, has 8 lines of symmetry as well as the 8 rotations, which is why I got the 16.
So you didn't count the rotations in for the squares?
Huh?
So these are only line of.
Oh, shoot. That should be 8.
Yeah, it should be.
That should be 8. Sorry, thank you.
That's the one we talked about.
Okay, yeah. So that should be it has 4 rotational symmetries and it should have another 4 lines of symmetry, reflection symmetries. Okay. So symmetry to me, it means symmetric means there are symmetries. The more symmetries there are, the more symmetric. Okay, so I want to go and transition a little bit. And instead of talking about symmetries, talk about something called isometries. Because all of the symmetries that we discussed could be classed under this umbrella of isometries. Okay, so anybody know what that means, in particular, Emma?
I'm guessing it has something to do with like reflective symmetry.
Okay, so reflective symmetry. So we would guess the rotations and reflections are special cases of isometries, but based on the context. Okay, so this is what I would call an isometry. An isometry, for the purposes of this talk right now, is a transformation of the plane that preserves distance. Okay, so if you apply the transformation to any 2 points, the images of the 2 points have to be the same distance apart as the original 2 points. Okay, now that actually lets in a kind of can of worms there. You could shift and not change the distance. But that wouldn't really count for what we were talking about with the figures, right? We were talking about transforming them and leaving them unchanged so that the image of the figure lied on top of the original figure. So shifting it kind of wouldn't fit with that. So what we're going to do is we are going to require that our isometry leave the origin fixed. So the origin has to get mapped to the origin. So if we were to apply it to these figures, we want the origin to be at the center of the figure, and we'd be transforming about that. Okay. Now, I know I didn't tell you exactly what my notation meant, but you can probably guess it from the context, right? D of PQ means distance between P and Q, and we want that to be equal to the distance between the images of the 2 points after we apply the transformation. Okay, so what I want to do in the first part of this talk is classify isometries. In other words, if we have an isometry that maps R2 to R2, what can we say about it? What does it look like? Can we kind of give a formula for the isometry? Okay, so we're going to take a point in R2 and we're going to get a point in R2. The input to the function is a point, the output is a point. So a very convenient way to do that is to use a 2 by 2 matrix. Okay, that is a function. A matrix is a function. It takes a vector for the input. So a 2 by 2 matrix would take a 2-part input from R2 and give you a 2-part output. All right. So a couple things. To create these matrices, what I'm going to do is just going to consider what the matrix does to our quote unquote basis vectors. So do we all know what that means? By we all, I mean Emma.
What?
Yeah, think about your Calc 3. We talk about the basis vectors there a lot. Right, and I guess you do that in physics too. Yeah, I, J, and K in 3 dimensions, I and J in 2 dimensions. So I would be the vector that goes from the origin to 1, 0. Sometimes we just call it 1, 0.
Oh, yeah, okay,
Okay.
yeah. I got it.
So if you know where this goes, then you're halfway home. But now you just need to know where does 0, 1 go, and then you've got everything. All right. Well, we want distances to be preserved. Okay, so this point has to end up somewhere on that circle because it started out distance 1 away from the origin, and it's got to stay distance 1 away from the origin. Right? The origin is a point, and the origin is getting mapped to itself. So we know that 1, 0 has to be somewhere on that circle. All right, now you might say, well, we can say the exact same thing about 0, 1. That has to end up somewhere on that circle too. That's true. 0, 1 does have to end up on that circle as well, but we can say a little bit more. Distances have to be preserved. So the distance from 1, 0 and 0, 1 has to be the same as the distance from the images. Okay, so 0, 1 ends up somewhere on the circle. No, switch it. 1, 0 ends up somewhere on the circle, let's say right here. The other basis vector, 0, 1, has to not only end up somewhere on the circle, but wherever it is, it has to be distance radical 2 away from the image of 1, 0. All right. How did I get the radical 2, Emma? Pythagorean theorem, right there's a triangle right there, side length 1. Hypotenuse has to be radical 2. This is why we got to get other students in here. That way I can ask other people questions. Okay, so what I did is I drew a circle centered at the image of 1, 0, and the radius of that circle is radical 2. That intersects the unit circle in 2 places, and those are the candidates for the image of 0, 1. Okay, so we can narrow it down quite a bit. There's more that we can say than just it's somewhere on that circle. It's got to be either up here or down here. All right, so let's look at some cases. Let's assume it ends up there. What can we say about this transformation? Okay, well, and so I don't have to do that and risk making that mistake again. I'm going to call that P from now on. I'm going to call that Q. Okay, so P is the first basis vector, or the point at the end of the first basis vector, and Q is the point at the end of the second basis vector. All right, so we're assuming that P of Q ends up over there. Okay, so this is actually something we talk about in tech and programming today. Right? Every point on the unit circle can be expressed in this way for an appropriate choice of theta. And of course, that's because the coordinate functions fit into the equation of the unit circle. The x coordinate squared plus the y coordinate squared equals 1, no matter what value of theta we have. Okay, now have you done geometry?
Like
How,
high
do you remember your constructions? Do you remember like your angle copy procedure in particular?
Like using a compass?
Yeah, using a straight edge and compass, copying an angle.
I mean, I could probably figure it out.
Oh, okay. So the reason I was talking about that is if we assign T of P to be those coordinates, then I'm claiming that T of Q has to be these coordinates, right? Plus pi over 2. Now you can kind of see it from the picture. You go, oh, well, there's a 90 degree right there. But how do we know that should be a 90 degree angle? Well, if we look back to how we made it, this is actually applying the angle copy procedure. right? I've got my vertex here at the origin, and I'm going from P to the origin to Q. Okay, this was distance 1, and they are separated by a length of radical 2 if you get distance 1 away from the vertex. And that's exactly what's happening over here. Okay, this was distance radical 2, and so we got that. So I basically just copied the angle. We call that O, let's call it O, QOP. I copied that to here. So T of P, O, T of Q would have to be the same angle as that first angle. Okay, so it really is a 90-degree angle. We could sit down. Okay, but if we know the angle here, then we know that. Okay, so these would be the coordinates of Q. Now we can apply some trigonometry. Okay, if Bailey was here, I would ask her, but she's not. So I'll just go ahead and do it. So we apply the angle addition formula. Okay, so the way I remember them is the cosine one goes cosine, cosine, sine, sine, and the middle is different. Why am I saying the middle is different? Yeah, because it's subtraction. The angle addition formula for cosine has a minus in the middle. This is just the way I remember things. It's not really a formal definition of anything, right? But we know this. Cosine of pi over 2 is 0, right? And sine of pi over 2 is 1. So that actually simplifies to negative sine. So the x-coordinate of T of Q is negative sine. And we could do a similar procedure there. Apply the angle addition formula for sine and get that the y-coordinate has to be cosine theta. So we know what happens to the first basis vector. It goes to cosine theta, sine theta. And we know what happens to the second basis vector. It goes to negative sine theta, cosine theta. Okay, so you haven't done linear algebra yet, but one of the tricks you probably will learn in linear algebra is if you know where the basis vectors go, you can write down the matrix for that transformation with respect to the standard basis. You take the destination of the first basis vector and you put it in the first column. And then you take the destination for the second basis vector and you put it in the second column. So this is the matrix that would give us that transformation. And it represents a clockwise rotation, no, counterclockwise, it even says it right there, a counterclockwise rotation through angle theta, okay? And this kind of agrees with what we were seeing before. Rotations give us symmetries. And we saw that the square had 4 of them, the octagon had 8 of them, the equilateral triangle had 3 of them, the circle had infinitely many. So for the circle, any value of theta will work. For the square, what would work? Pi over 2, pi, 3 pi over 2, and 2 pi. And those are the only ones that'll work for the square. Okay, so now I kind of left something out. What did I leave out? I started out with saying, okay, well, what if Q ends up over here in the upper left? What else did I haven't addressed something yet. Right, it could have been in that other place, right? There were 2 options. Okay, so we don't necessarily know that our isometry has to look like this. This is one of the possibilities. If the point Q ends up over there, that's what our isometry would look like. But what if it doesn't? Okay, so here's case 2. Now we could apply the same reasoning and get that this angle from T of P to the origin to T of Q has to be 90 degrees again. Okay, but we've kind of gone the other way. And of course, by convention, we have a way to make sense of a negative angle. A positive angle would be rotating in the counterclockwise direction. A negative angle would be rotating in the clockwise direction. So we can say that the coordinates of the target for Q would be theta or cosine theta minus pi over 2 and sine theta minus pi over 2. All right, so what do we do? Right, same thing we did before. We apply the angle addition formula, or I guess it's the angle difference formula, really. But they kind of look the same, right? It goes cosine, cosine, sine, sine. Now there's a plus in the middle. So what we're going to end up with is that the x coordinate goes to sine theta, and the y coordinate is going to go to negative cosine theta, because the angle difference formula for sine has that minus in it. Okay, so that is the second variety of transformation that will give you an isometry. Okay, now I'm claiming down here that this transformation represents a reflection over a line through the origin that makes an angle of theta over 2 with the x-axis. Okay, it might not be obvious from the matrix because it looks basically the same as the other one. The only difference is that instead of the minus being in the upper right, the minus is in the lower right. Okay, so let's think about the picture in this way. Okay, so I've got my point P, and there's the target, P of P. I've got my point Q, and there's the target, T of Q. Now, the angle theta was the angle between P, the origin, and the target for P. This is the angle bisector for that. Okay, so these 2 points are found by reflecting over that line. Anything that was below the line of reflection ends up above the line of reflection. And things that were above the line of reflection end up below the line of reflection. Okay, you might not be able to see it in this picture, but that really is a 90-degree angle right there, going from here down to here. So this is equidistant. Okay, that's the bisector of that line going through Q, and it intersects the unit circle at that other point, T of Q. So that really is a bona fide reflection about that line, and that actually covers our basis that we had from before, because we were saying, okay, what makes these figures symmetric? Well, how many ways can you mess with the figure but end up keeping that figure on its original footprint? You can reflect, you can rotate, and we've covered reflections and rotation with these types of matrices. Okay, so now after all that, it's not really about distance. Okay, it's nice to think about distance, and it's a kind of very elementary concept to wrap your head around, but there's in a way there's something more fundamental going on behind the scenes, not just distance. Okay, it's really about inner products. Okay, so of course we know the distance formula for stuff in R2. Right? If I define my point P to have coordinates P1, P2, and Q to have coordinates Q1 and Q2, if I want to find the distance, I would take the difference between the first coordinates of each one, square that, difference between the second coordinates of each one, square that, add them together, take the square root. Oh, there's a typo here too, yeah. Another thing I gotta fix. What's wrong? I gotta have a square root up here on the left. Underneath, that is the inner product of P minus Q with P minus Q. Okay, but I don't get distance until I take the square root. So I'll have to alter those two things. The other thing I got to fix is I said the square only has 4 symmetries and it really has 8. Okay, I should probably keep a little running tally of my stuff to fix. So space pen. Okay, so fix symmetry of squares, and then I don't know what I'll call that. I'll call that inner product first page. Okay. So everything we say about distance can be said using inner products. Okay. Now I am being a little bit fast and loose here, going between points and vectors. So just forgive me. I do that a lot. Okay, so if we follow, let's say, I think Larson uses this notation. He uses brackets for his vectors, right? So we should be familiar with that from our calculus 3. So I suppose I should have done this before I used inner product. We're just defining what inner product is, right? So v dot w would be product of the first two things plus the product of the second two things, which is exactly what we would get over here, right? P minus Q, well, I would just take the difference between the coordinates. I would get P1 minus Q1 times P1 minus Q1, in other words, that plus P2 minus Q2 times P2 minus Q2. Okay, but the way I like to look at inner product is this, okay? I treat my vectors as column vectors because, well, that's the right way to do it. And if you treat them as row vectors, you're wrong. Okay, but so I treat them as column vectors. What does the T mean? Transpose. Okay, so if you have a matrix, you can do tons of operations on a matrix. You could find the determinant of that matrix. You could take so determinant will give you a number, it'll give you a scalar. If you take the transpose of a matrix, it gives you a new matrix. So we are interchanging the rows with the columns. So the first row becomes the first column becomes the first row, et cetera, et cetera. So if V is a column vector, the transpose would be a row vector, because it only has one column, so that becomes only row. And then we just do the matrix product, right? We take the entries in this row times the entries in that column, kind of component-wise, we add them all up. So we have V1 times W1 plus V2 times W2, and you get one single element. If you remember that little trick, right? This is a 1 row, 2 column matrix, 1 by 2. This is a 2 row, 1 column matrix, 2 by 1. 1 by 2, 2 by 1. The inside numbers match, so you can do the product. The outside numbers tell you the size of the product that you're going to get. You're going to get a 1 by 1 single number. Okay, so we can rephrase the inner product to be thought of in terms of matrix multiplication. Okay, so why are we talking about this? Well, we can show that if a matrix M preserves inner products, then it preserves distances between things. Okay, it's not that hard because the two are just about interchangeable. Okay, so I'm just going to ask you to believe me on that. Okay, why did I switch from, because I was calling the transformations T a while ago. In fact, I even said T and then gave a matrix. Why did I switch? Because I wanted to use T for transformation. Why did I switch to M?
They're the same thing.
Matrix multiplication.
Yeah, matrix multiplication. I was thinking I didn't want to have T transpose.
Oh,
So now that I've started bringing in these transposes, I'm going to call the matrix M to avoid having T transpose. Especially if we talk about T transpose, then it's all going to go crazy. Okay, so if I say a matrix preserves inner products, this is what I mean. That if I apply the matrix to each part, I would get the same thing as if I didn't apply the matrix at all. Okay, so the inner product of the images of the two vectors is the same as just the two vectors original. So that's what I mean by preserves inner product. Okay, well, what would we want that to be? Well, let's think of this in terms of the matrix definition that we had earlier. It was the transpose of the first thing times the second thing. Okay, well, if the first thing is MV, we should do MV transpose times MW. Now, something you'll learn in your linear algebra class, the transpose of a product is not quite the product of the transposes. You have to switch it. Okay, so MV transpose is equal to V transpose M transpose. Okay, so what we really want, so basically what we want this to end up being this, which is equal to the inner product of the two. So what are we really saying we want to happen here? Right, we want that to basically go away. Now, you gotta be a little bit careful about when you say go away, do you mean it's 0? But we don't want that, because then we wouldn't get v times v dot w, we get 0, which we don't want. So we want that to be the identity. That would be nice. Okay, so that being said, if n transpose times n is the identity, that's equivalent to saying this. Okay, so you talked about inverses in abstract algebra, right?
Are we doing it
We
right now?
just doing that.
Oh, okay, all right, so this is the identity for matrix multiplication. You multiply by that, it doesn't do anything, so if you have an element that multiplies and gives you the identity, well, that's the inverse, that's what the inverse does. But not saying anything about how to compute it or anything like that, but if a matrix has this property, then it has an inverse, and this has to be the inverse. Okay. So let's look at the matrices we came up with. This is one of them. Okay, so let's look at this product. M transpose times n. Well, M transpose means that the rows become the columns. So the first column should be cosine theta, negative sine theta. And the second column should be sine theta, cosine theta. All right, now we'll do the matrix multiplication. Entries in the first row times the corresponding entries in the first column. Cosine theta plus sine theta. Pythagorean identity, we get a 1. First row, second column. Negative cosine theta sine theta times sine theta cosine theta. I'm sorry, plus sine theta cosine theta, those cancel each other out. They had opposite signs, so you get a 0. Once again, a 0. Two negatives give you a positive, sine squared theta plus cosine theta, and you get a 1. Okay, so 1, 0, 0, 1, that's the identity matrix. Okay, so we call these orthogonal matrices. Okay, so the columns are forming what we call orthogonal vectors. You remember what that means?
90 degrees.
Right, 90-degree angle. Okay, good. Because sometimes that has different, sometimes that's called normal. If it makes a 90-degree angle, especially in calculus 3, like the normal line or something like that. So sometimes we use that word, but I want to avoid that because that has another meaning in linear algebra. Sometimes it means norm 1. But
I already learned them.
Oh, okay.
More knowledgeable. Normal is a very.
Yeah, yeah, and then in modern algebra, it means another thing entirely. Okay, so these are called orthogonal matrices. Basically for that reason, when you do that product, you're kind of taking the dot product of the various column vectors with themselves in the entries. Okay, so let's talk about generalizations. So we're talking about the plane right now. So I can think of a couple of ways to generalize. We could go and bump up higher dimensions. I don't think that's the first thing I did. What the heck was the first thing I did? Okay, this. Okay, I knew it had something else in it. Okay, so this is my, have you talked about groups yet?
Yeah.
Okay, great. So you know the 3 things. I should have put delays on this. On the 3 things. So you've got to prove that your group, or if you're going to prove something as a group, you have to prove it contains the identity. Okay, now what was the criteria to be an orthogonal matrix again? Okay, right. You had to have an inverse, and the transpose of your matrix had to be the inverse. So you're an orthogonal matrix if your transpose is your inverse. Now the transpose of the identity is the identity back again. And of course, the identity times the identity gives you the identity. So the transpose is the inverse for that matrix. So if M is orthogonal, then N inverse is orthogonal as well, because transpose of the transpose gets you back where you started. It's, oh gosh, there's a, it's got, what is it? Idempotent? Is that? Warren probably knows if an operator, if you apply it twice, it's like you did nothing.
That sounds about right.
Yeah.
Okay, so the operation of taking a transpose is an idempotent operation. It undoes itself. It's like taking the reciprocal. You do 2/3, you take the reciprocal, you got 3 halves, you take the reciprocal again, you're back to 2/3. And we know that n transpose times n gives us the identity. It's going to work the other way too.
Is that what you were looking for in class, the transpose?
Yeah.
Yeah.
You read that.
Okay.
It's not conspiracy.
Yeah.
More than half, I know.
Okay, and the last thing here is I am showing that the set of orthogonal matrices is closed under products. You have to prove that if you take 2 of them and multiply them, you get a new thing that is also meeting the condition. There is a kind of have you taught them the 2-step way to do it? It's not really a 2-step way to prove a group. Usually prove the identity is in there, and then prove if X and Y are in there, then XY inverse is in there. So it's not really just a 2-step thing. It's kind of cheating.
Today, actually, we did subgroup test, 2-step and 1-step.
Oh, okay. So-
You do have to show it's not empty though.
Yeah,
Yeah.
Well, you would show that empty.
yeah. That's usually the way I show it's not empty.
Right.
So let's see. So let's suppose n and n are orthogonal, meaning n transpose equals n inverse, n transpose equals n inverse. We want to look at the product. We want this to be the identity. Okay, so I knew this was my target. Now I can't just jump right to my target. I can't just say that's working. I've got to demonstrate why it's working. Well, property of transpose, right? You can take the transpose of each one, but you got to switch them. So M transpose, M transpose. So where'd it go?
It's the inverse of itself.
Right, this is M
I
inverse.
mean, yeah.
This is M inverse. So they multiply to the identity. So I guess I could have put another step in there and said the identity is in there, but we know what's going to happen there. And then the same thing applies to N because N is also orthogonal. So the product is orthogonal. Okay, so orthogonal matrices form a group. So one generalization, you can kind of take it to another level. We're not talking about linear algebra anymore. We're talking about modern algebra. Okay, let's do other generalizations. Okay, this I thought was kind of fun. Okay, so let's take it up a dimension. Okay, so we're not talking about transformations in the plane. We're talking about transformations in 3-dimensional space. Okay, and let me see. Do we have any spheres? I should have brought my big sphere. Do we have any little spheres? Oh, I think I know where to come off. Okay. So. Oh, it's clear. This will show up great on here. Okay. So let's see. Little tiny sphere that nobody out there can see. Okay. So instead of talking about the plane where we talk about the unit circle, this is like the unit circle. It's the unit sphere. Okay, centered at the origin. So certainly if you keep the North Pole and South Pole fixed and you rotate that way, well, then you have a fixed axis. The north-south, the axis going through the North and South poles are fixed. If you, let's say, fix the East and West poles and you do a rotation there, then you have a fixed axis. Well, that thing that we just showed on the previous slide, that didn't really rely on those matrices being 2x2 matrices. We could apply that no matter what this, as long as they were square and orthogonal, that would work. So if I take 2 3x3 orthogonal matrices, the result should be orthogonal. So what I'm thinking is, okay, what if I do my North and South Pole rotation? What if I rotate that way and then rotate that way? That should be an orthogonal matrix. And it's not obvious to me that there was a fixed axis when I applied those two one after the other. Okay, so this would be something that's kind of interesting to prove. So let's look at these calculations here. Okay, I'm looking at the determinant of m minus I. So it looks like I'm finding eigenvalues, but there's something missing. There's usually something else in here. Right, we usually put a lambda in here. Okay, now if lambda were 1, then I would be trying to find some. Basically, what I'm trying to do is, and I'll get to the punchline later, but so keep thinking about that eigenvalue construction, which is something you'll learn in linear algebra. Okay, so what am I doing here? What's going on there?
Substitution.
Right, that's a substitution. We're assuming M is an orthogonal matrix. And determinant 1, that's up there too. That means it's not a reflection, basically. Okay, so M transpose times N equals the identity. So I can put that in. Now what I'm doing here is I'm factoring out an M on the right. Okay, this part's a little tricky. Why can I just drop it? There's only I minus M here. It just went away.
Determinant of a product is the product.
Right, the determinant of a product is the product of the determinant. So the determinant of I minus M transpose times M is equal to the determinant of I minus M transpose times the determinant of M. Determinant of M is assumed to be 1. So that second factor, determinant of M, goes away. Now notice another tricky thing I did here, right? This is I minus M transpose, and then this is I minus M transpose. If I say it fast, we lose the subtlety. This is I minus M and then the transpose. What's going on there?
Because I is the identity.
Right, I is its own transpose. Okay, so I think it works, right? Because you're doing 1 minus, so your first row, it would affect the first row, first column, second row, second column, third row, third column. It would affect you down the diagonal if you do I minus M first. So those would all stay in the same position. Okay. Now, this is also tricky linear algebra. Okay, we got to think about how the row operations affect the determinant. Okay, so if I switch rows and columns, I'm going to mess with the sign of the determinant typically. Although if you do this in 2 by 2 land, it kind of sweeps something under the rug. Okay, because it's 3 by 3, when I do all the switching, switch the row to the column, I change the sign of the determinant. I change it 3 times. So that's why this -1 cubed is out here. Okay. So the dimension of the matrix basically determines this. Okay, if you have an odd matrix and you take the transpose, you're going to change the sign of the determinant. If you have, let's say, a 2 by 2, nothing would happen.
Determinant if matrix is the same as its transpose, so I'm missing something.
Huh?
Yes, because.
Yeah. I need one more step. Sorry.
Yeah.
I have to add an additional step. Okay, so the determinant of I minus M transpose would be equal to the determinant of I minus M,
Okay.
which is equal to, now let's look at
Yeah,
I really want to
that's
get
the step I thought you were.
M minus I. That's what I really want. So that's the negative of this. And this is where the size comes into play.
That's when you.
Because it's taking the negative of the entire matrix. So that's taking the negative of 3 rows. And that's why we need -1 to the 3.
Yeah.
Okay. I was kind of trying to make my argument more compact and I smushed some steps. So that's another thing to fix. Fixed axes.
Well, just put one more line where you have determinant of the opposite of M minus I or something like that.
Right. Yeah. That
Well,
would
maybe
work.
2 rows. two more things.
Yeah, so I definitely need this here, because I want that to be my punchline,
Yeah.
right? Because I
Okay.
started out with m minus I.
Yeah.
And then I have determinant m minus I again, but it's negative. So that tells me this determinant is 0, because that's the only number that's equal to is negative. And that tells us that there is an eigenvalue of 1, which would have an associated eigenvector, and that's your fixed axis, or your fixed axis. So when you get into your linear algebra, eigenvalues are very nice, eigenvectors are even nicer. They're basically things that get mapped to themselves. So if you had an eigenvalue of 2, the associated eigenvector would get mapped to, let's say the vector was v, you apply the transformation, you would get 2v. It tells you how far it stretches the vector, basically. So if it's got an eigenvalue 1, it just keeps the vector stable. So putting that stuff together, we can show that in R3, if you're dealing with a rotation, there has to be a fixed axis, even if it's one rotation followed up by another rotation. Okay, let's generalize more. We talked about fixing inner products. Okay, well, the usual inner product is a special case of something called a bilinear form. Okay. Now, big boy linear means that it breaks up over addition, right? So a linear transformation, T of A plus B is equal to T of A plus T of B. So it's linear in this factor, it's linear in this factor. That's why it's called bilinear, okay? Now, the thing that gets hidden with the usual inner product is there's a little identity matrix that we normally don't write sitting there in the middle. So a generalization of that would be put different matrices in the middle. Okay? So generalize this by taking other choices of matrices. We'll redefine our inner product to look like that. Okay, so if we're playing this game of we want the matrix to preserve the inner product, we are no longer looking at M transpose M equals the identity. Okay, if our inner product now has this factor of C in the middle, and we want this inner product to be equal to this over here, what we're really saying, oops,
You just have some superscripts.
switch those, right? What we're really saying is this down here, M transpose times C times M should take you back to C. That's what we want to have. Okay, well, who the hell would ever do something as insane as putting a different thing in the middle? Okay, well, I'm glad Warren was here, right? Minkowski 3 space, okay? Minkowski 3 space, well, three, yeah, kind of 3, right? It's really 4-dimensional space-time. The time coordinate gets treated a little differently than the space coordinates, okay? So that's your time coordinate right there. Sometimes people put a 1 up here and negatives down there. I think if your matrix preserves the 1, it's going to preserve the other. It's just differing by a diagonal. Okay, so this has applications to things like relativity, stuff like that. Okay, so the transformations that preserve stuff in space-time boil down to saying, okay, what transformations preserve this? And in our summer course, we called that the Lorentz group. Okay, started looking at a special case of like Lorentz 2 space, where you just have one physical dimension and then your time dimension. So it's a smaller matrix, and we can classify the transformations a little more easily. But we did go and look at the 4-dimensional case as well, though not in as much detail. Okay, and we could prove in a very similar way that if you have a matrix C defining your bilinear form, matrices that go n transpose Cm equals C, the matrices that have that property, they also form a group. The identity is easy to prove. It always works, right? The identity transposes the identity, so identity C times the identity equals C. So that's it, okay? A little bit trickier to prove that the inverse also works, but it can be done. And then you'd have to prove the product works. That one's really easy because of the switching when you do the transpose. So then you get the matrices in the right place. Okay. I believe these are also called, they're not orthogonal matrices anymore. It's a group of symplectic matrices. When you're doing a generalized inner product like that. Okay, so I think that takes us to about 50 minutes. So any questions?
Well, we hope you enjoyed that and learned something from it. I will be posting a link down in the description of a typed out version of the slides with the minor mistakes that were pointed out corrected. The remainder of the time was spent dealing with some questions and comments concerning Minkowski spacetime in particular, but I would also like to point out some resources that we made use of. This was the text that I referred to for our summer course way back at the beginning. I mentioned JC would be familiar with this. Well, this is the book we used. It was Lie Group's A Problem-Oriented Introduction Through Matrix Groups. It's by Harriet Palatsek, and it's available from the MAA. That's one of several accessible introductions to matrix groups that have come out in the last decade or so. Another one is right here, Matrix Groups for Undergraduates by Christopher Tapp. This is published by the AMS. And Dr. Doherty did mention a few books that he has been interested in about Minkowski spacetime. And this is the first one, The Geometry of Minkowski Spacetime. And he also suggested I look at the mathematical methods of classical mechanics. So if you're looking for some additional resources, those would be places to check.